second time. So, nope. We're just making fun of all the new arrivals. But this is completely, I joke, but this is completely an optimization problem, right? I have a limited amount of time, and I need to eat my lunch, and then I need to lounge around. So how do I get to the talk in time while still optimizing my time outside the talk? And there's all sorts of these sort of optimization problems. And this is DevOps. There's lots of really good talks going on right now. So I think the first question to start with is, why are you all here? Why is optimization interesting? Why would anybody want to optimize? It turns out optimization is actually a business thing, and it's about your users, because users get really cross if they have to use something slow. And that crossness, that irritation, turns into lost revenue. So Akamai did some studies, or actually, sorry, this one is a Google one. So Google did a study, and they found that if they had half a second extra on their search time, they had a 20% drop in traffic. That's huge if your business is based on generating traffic. And Akamai did a study, and they found that if you had 100 milliseconds latency on your page, which isn't very long at all, again, you're looking at a 7% lower conversion rate. So this is something where we can actually really quantify, I need to go faster, because if I don't go faster, my business is going to lose money, and then I'm going to get fired. If you're in something like trading, then the impact is even more dramatic. Hopefully, hands up if you're doing high-frequency trading. Good. Hopefully, if you're doing high-frequency trading, this is not your introduction to Java performance. But high-frequency trading, it really, the whole business is built on the efficiency of the platform. And so for those ultra performance-sensitive systems, if you have a 10-millisecond delay in a trading platform, that's so small you can barely measure it, it turns to a 10% drop in revenue, which, again, the amount of revenue that these companies are generating is huge. So it doesn't really even bear thinking about how much money is involved. So with that said, clearly, optimization makes good sense. It's something we should be doing. So then the next question is, this optimization thing that I now think I should be doing, what exactly is it? And usually when we say optimizing, we're trying to sound really clever, but what we really mean is just make it go faster. But it's not actually that simple. We need to think about, there's not sort of this universal faster. We need to think about, who is it going faster for? Under what circumstances is it going faster? What is it doing? What are people doing when it wants to go faster? So I work for Red Hat now, but for 20 years I worked for IBM, and for 5 years of that time I worked in a team called the IBM Garage. And one of the things that we did in the Garage was we brought design thinking to every problem. And design thinking is really another way of saying human-centric design. And the interesting thing about it is it sounds really fluffy. It sounds like it's just about, the pictures on the page, but it's really not. Thinking about people and what they're trying to do is important for security, it's important for performance, it's important for all these things that seem really technical. So when we think about performance and optimizing, even though it seems it's about computers, we have to remember computers are the side effect. It's actually about people. But having said that, there's all sorts of different things that people could be doing or trying to do that we maybe want to make better by doing some optimizing. And when we say performance, there's a whole bunch of quite distinct things that we mean. Probably the first one that comes to mind is throughput. So this is something that's usually something like transactions per second. How much data, is sort of going through this system. Sometimes what we actually care about is more like latency. How responsive is this system? When I go to the system, does it respond quickly? As a developer, one of the things that we maybe care about is something like startup time. Or even as a user, actually, you may care a lot about startup time if there's a serverless backend and you have to wait for your page to be served for that serverless backend to come up. Or things like, response time, startup time, those kinds of things. Maybe it's not actually how long it takes to start up, but how long it takes to get really to its full efficiency, so something like a ramp-up time. There's other things that we can think about, too. For example, capacity. So capacity we think about most often when we're thinking about the footprint of a system. If my thing is so huge that I can only run one of it on a virtual machine, and I have to have a whole bunch of AWS instances just to get a decent capacity, that's maybe not so good. Capacity, that might be a footprint issue, or it might be a CPU usage. When I run Slack, it's a lot better now, but it used to be that when I ran Slack, it took 100% CPU on my machine. So I couldn't do anything else on my machine, and I never actually got one, but I needed one laptop to run Slack and one laptop to do all the rest of my work. So there's a capacity problem there. A sort of a related idea, which is sort of the opposite but sort of the same, is utilization. Utilization is a really funny one to think about, because when we say we want to make utilization better, we could mean, I want to make utilization higher. I want to be really efficient with this system. So for example, mainframes are incredibly efficient, and one of the ways in which they're efficient is that they run at about 95% utilization, something that an x86 machine can't even dream of. So that high utilization is a really good thing. But on the other hand, when I'm looking at something like Slack, what I really want is low utilization. I don't want it to be at 95% of the CPU. I want it to be at 2% of the CPU. So again, even when we use the word, we then need to be really careful to think about, OK, well, but which direction do I want to go in? And of course, where this gets really fun is you might say, OK, I've got my requirements. I would like, please, high throughput, low latency, excellent capacity, and excellent utilization, whatever that means. But it doesn't work that way. Sometimes these things you can optimize together, but usually they go in opposite directions. So you're making these trade-offs. You get better throughput, but at the expense of worse latency. And the classic example of trading off throughput against latency is this one. Never underestimate the bandwidth, by which we mean throughput, of a station wagon full of tapes hurtling down the highway. So how many of you had heard this before? About half, yeah. I love this because it's so counterintuitive. And so when I was preparing this talk, I went and I looked at the history of this quote, and it is actually a real incident. It used to be that NASA had 2 sites, and they were connected by a big fat data pipe. And then that data pipe broke. And so they had to get the tapes that had star data or whatever it was from one site to the other. And so what they did is they took the tapes and they put them in this white station wagon, and they sort of went down the highway. And the latency was pretty terrible because they had been accustomed to this instantaneous connection, and it took an hour or whatever to get the cars down the highway. But they managed to transfer so much more data than they ever could have got along their little pipe. So I don't think they stayed that way because the latency was terrible, and that was an important performance characteristic. But they did get a good result there. And the thing about all of this that makes it extra tricky is, of course, even if we think we're optimizing for throughput, it could be that the requirements change. Unless we're sort of one of those, I have no agile here. I'm going to engrave my requirements in stone. Things change. So a colleague told me a story of a bank, and they had some functions running on a mainframe. And the way in which it operated was that at the end of each shift, the teller would push a button, and it would send a little bit of workload to this mainframe. And then the next teller at the end of their shift would send a little bit of workload. And one of the other teams in the bank saw this API, and they were like, that API looks really handy. We're developing a new mobile banking platform. That API is going to be just what we need. So all of a sudden, instead of having 1 or 2 usages an hour, they had all of the bank's clients with mobile phones, and every time it refreshed the page, which was every few seconds, it would hit this API. So all of a sudden, the volume of traffic just went through the roof. And this poor server, it started to gently smoke in the corner, and then it smoked a little bit more, and then eventually, after enough traffic, it just completely fell over. So it wasn't that the performance had been wrong for the original use case, it was just that the use case changed and nobody told the authors of that system. But even if we did engrave our requirements in stone, the fact is the world around us changes. The context in which we operate changes. So the cloud, for example, has completely changed the performance requirements for our system. And all of a sudden, that XMX argument that we used to not really pay much attention to, except for maybe making it as big as possible to try and increase our utilization, that now is money. So we really care a lot about footprint. So way back at the beginning of my career, I was a Java performance engineer. And I worked on OpenJ9, except it wasn't OpenJ9 at the time, it was J9. And so we always knew it had quite good performance, but nobody else really talked about the performance. And so I was really, really happy a few years ago to all of a sudden see conversations happening about how great OpenJ9 was. But the interesting thing about the performance is that it's not like OpenJ9 is better in all circumstances. It's that for some things, it's better. So for example, when you look at startup time, OpenJ9 starts in about half the time as Hotspot. If you look at footprint, OpenJ9 has about half the footprint of Hotspot. If you're looking at throughput, then it's a more mixed picture. If it's just after starting, OpenJ9 has better throughput because it's starting faster and it's ramping up faster. So even here, OpenJ9 is better. Once you get to about here, Hotspot is better. So probably if any of you have been in any of the Quarkus talks, even though that's not a Quarkus story, that's an OpenJ9 story, it's going to sound familiar. So Quarkus is really, really amazing at having startup speed and footprint. But there's a trade-off. With Quarkus, the trade-off is not that overall performance, it's flexibility. It's front-loading more things, and so you've got a slower build time in exchange for going way, way better at runtime. But if you're going to be doing something like really reflection-intensive coding, it's maybe not for you. And I work in the Quarkus team now, but before I joined the Quarkus team, I knew about Quarkus, obviously. And I was talking to some of the Quarkus people, and they told me a story which I really loved, which is that they were at a conference, and they were on booth duty. And because it was a conference, it was sort of all hands on deck. And so one of the people on the booth was one of the project managers. And I've discovered at Red Hat, actually, the project managers are quite technical. But this project manager, I think, was probably still not the most technical member of the team. And so the project manager was, sort of demonstrating Quarkus, and so someone would come to the booth and they'd go, look, 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 amazing, amazing, and then the next person would come, look, 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 amazing, amazing. And because they weren't playing with Quarkus every day, they forgot an important part of doing demos, which is that you're supposed to shut the thing down after you demo it. So they would sort of spin a Quarkus up, and then they'd spin another Quarkus up. And they looked at their laptop at the end of the day, and they had 120 instances of Quarkus running. But the best thing about this story is that actually, it honestly didn't matter. Their laptop showed no ill effects from running 120 Quarkuses concurrently while trying to, to talk to people. With Quarkus, one of the things that has a lot of people really quite excited about Quarkus is the native compilation, because that's where you get the sort of super ridiculously awesome startup speeds, and it starts up in 40 milliseconds, and it only doesn't really seem to use any memory at all. And I think the Quarkus team, I think sometimes sort of have a little bit of a conversation to say, yeah, but actually it's really quite good, even if you just run it on OpenJDK as well. So then the question is, okay, but this native mode, it looks amazing. Why wouldn't I want to use that? Which is better? And by which is better, we really mean which is faster. So you can have GraalVM, then Quarkus, that's the framework, and then your application. Or you can have OpenJDK, and then Quarkus, and then your application. How do you choose between them? Again, it's trade-offs. If you're doing something that's ephemeral, like serverless, then you definitely want to optimize for that startup time. Serverless doesn't make any sense at all unless you can have a fast startup time, which is why Node.js has such dominance for serverless. On the other hand, if this is something that you're not actually doing serverless, that doesn't make sense for your domain, and you're going to be running your application for a long time, you're probably going to be better off with OpenJDK. Because even though your startup time is a little bit longer, things like the JIT will actually give you better performance overall. And when I worked in Java performance, one of the conversations that we used to have all the time was, why can't I do ahead-of-time compilation? And we always used to sort of patiently go back and say, look, it seems like it would be faster to do ahead-of-time compilation, but the JIT gives you more than it takes away in terms of performance. Really, you do want to do the dynamic compilation. And it's sort of a similar conversation now, except it's a little bit more balanced. Sometimes you do want to do ahead-of-time compilation. Sometimes you still don't. But with this sort of neat story, there's a third scenario that I haven't covered, which is, what if your application is running for a long time, but it's not actually doing anything? It's not like there's workload going to it. So the correct answer in this scenario is, well, then you should be using serverless. But assuming you're not, if your long-running application actually got forgotten, then the conversation's a little bit different, because then probably at that point you want to be back to thinking about using as few resources as possible. So you want to be back to having that small footprint. But this is a really tricky thing to optimize for, because no one ever says, I'm going to optimize to work really hard writing this application and then deploy it and have no one use it and then have management forget about it and I'll leave the company and 5 years later it's still running. But the fact is, this is actually how a lot of our systems end up. Research says that between about 25% and 30% of the applications running are zombies, which basically means they're not doing anything useful at all, but either everybody has forgotten about them, or people are too scared to shut them off. And these things can end up being really persistent. There's lovely stories about things like, there was a team, they had a server, and they felt like it wasn't useful, and they wanted to shut it down, but they couldn't physically find the server. And they eventually found the server, and it had been bricked into a wall. So they had to get a sledgehammer and remove a wall in order to actually find this server to shut it down, which is how you get zombies. OK, so whichever you're going to do, optimization's important. You kind of know what it is. What next? How do you do it? Well, this bit in principle is really easy. The rule of performance optimization is you find the bottleneck and you fix it. So Friday the 13th, what could possibly go wrong? Well, it turns out that there's a lot of pitfalls on this, let's find the bottleneck and fix it. And the first pitfall is intuition. This application, I feel sure I know what the problem is. It's no. Performance optimization, I hate to say this, ideas are good, but if you're doing optimization, ideas are bad. This is not the place for ideas. You really need to measure. So measure, don't guess. Even if you're sure your guess is good, even if you're a performance guru, Don't guess, measure. But there's another trap, which is that you need to measure the right thing. You need to think really hard about what your users care about. And this is the second pitfall of optimization: numbers. So I think some of you probably saw me on the keynote stage on Wednesday looking at a number, completely struggling to deal with this number because numbers are hard. And I should say, I do have a PhD in quantum physics, even though I can't actually do fractional multiplication. So, but that's actually not the hazard of numbers in this context. It's not that numbers are hard. It's that numbers look hard. And we see a number and we go, ooh, a number. That's not fluffy. That's correct. But actually, numbers aren't magic. It's not like if you have a number, you're automatically doing the right thing. I want to take a little bit of a digression away from programming into sort of more business science, but I think this is something that's really interesting that more of us could do to think about, which is, how do you measure things? And there's two kinds of indicators. There's leading indicators and lagging indicators. Lagging indicators are the things that we care about. How much money is my business making? How much money have I got in my bank account? Are users happy? They're really easy to measure. How much money have I got? I've got that much. But the problem is, they're kind of hard to change. How much money is my business making? Well, we want to just make more money. Well, no, you can't do that. You have to figure out how to make more money. Leading indicators, on the other hand, they're really easy to change. How much CPU have I got? How many people have I hired? They're predictive of a thing we care about. So for example, I mentioned how happy are our users. How happy are our users is probably a leading indicator, actually. So if our users are happy, then we'll make more money. The problem with leading indicators is that it's really hard to figure out what they are. What thing do I need to change so that I can change the thing that I actually care about? So I'm going to show you a few little performance experiments, but I want to give you a big caution, which is that these are for entertainment purposes only. Do not try these at home. These are really bad experiments, and even if they were good experiments, the performance experiments that I do will not be the right performance experiments for you. So way back when, I did, IBM paid for me to do an MSc, and so I said, OK, I'll do an MSc. So I had to write a thesis for it, and I wrote it about what I was doing for my day job, which was garbage collection. And at the time, there was this bad advice, and what really annoys me is you still see this bad advice now, which is, if you want to make your system better, reduce the amount of time spent in garbage collection. And this is bad advice because garbage collection can actually make your application go faster. One of the things that garbage collection does is rearrange objects on the heap. And objects that are physically close to each other will end up close to each other in the cache, which means access between those objects will be fast, which means your application goes faster. And we forget that when we say, let's just optimize away garbage collection. So in 2007, I did these experiments. And that's probably, I can't even read that, and I'm here, so you'll never be able to read that. But what that's showing is pause times for two configurations of an application. And this is showing throughput for the two applications. So there's the pink line and the blue line, and you can see that the blue line is spending way more time paused than the pink line. But yet, the blue line actually has more throughput than the pink line. And what I'd done to make that happen is I told the blue system to do a heap compaction every single garbage collection. And this is obviously a terrible idea because I was a bit concerned that his ceiling was going to collapse, which would be make performance optimization the least of our worries. But I think normally you would never go out and say, I'm going to tune my system by doing a compaction every collection, because your pause times go through the roof. But actually, the ridiculous thing is that even though your pause times go through the roof, you still get better throughput. So when I was writing this talk, I thought I will recreate this experiment. I didn't have access to the same benchmarks, so I used DayTrader and JMeter, and I set up a little system, and I put in the arguments that I'd used before, which was compact every GC. Then I realized I'd forgotten to set the property to the GC policy to the one where that would make a difference, because things have changed in 15 years, so I did that. And then I realized it still wasn't quite working, so I put it in a really constrained heap to try and force it. And then that wasn't working, so I made the heap a little bit bigger to try and change it, and then that wasn't working, so I made the heap huge to try and change it. This, by the way, so this is the bad science part. You should never, ever, ever try and design your experiment to show the thing that you're trying to prove. The experiment is there to disprove the thing that you're trying to prove, otherwise it's bad science. So eventually, I managed to get there by changing the things in my system. So I ended up back with my kind of simple arguments, and I did 2 sets of experiments, and so this was in GCMV, plotting the results. In the first experiment, my total GC time was 21 seconds, so pretty big. 4% of my time was spent paused. In my second experiment, GC time was only 12 seconds, so you can see it was doing fewer GCs, and they tended to be shorter. And so it meant that only 3.6% of my time was spent in GC. I'd made a savings in my system. It was spending less time in GC. So who thinks this one is the better case? Hands up if you think this one is the better case. OK. Who thinks this one is the better case? 2 hands. Who's afraid it's a trick question, so you're not going to say anything? Because, yep. Good work. You're right, it is a trick question. So you can see that a little bit if you dig into it a bit more, because the reason this one spent so little time in garbage collection was because there was only 13 gigabytes of garbage to collect. This one spent more time in garbage collection because it collected twice as much garbage. Why was there so much more garbage? Had I made some really clever optimization to the object layout in my heap, or done some optimization to not use JSON or something? No. This one was doing half the number of transactions per second of this one. So basically, if I do less work, I collect less garbage, so my garbage collection is cheaper. Duh. So going back to that language about indicators, this here is my leading indicator. I think, until I work out it's a trick question, that if I reduce my garbage collection time, I'm going to be better off. So I do everything I can to reduce my garbage collection. This here is the lagging indicator. So this is the thing I really care about. How much am I actually doing? But of course, we know that this is a pretty bad leading indicator, because instead of making my system better when I did less garbage collection, it made my system worse when I did less garbage collection. And actually, this lagging indicator, it maybe isn't even a great indicator either. Maybe this is a batch job running overnight, and I'm paying a lot of money for really high-powered instances, but it's a batch job, so I've got 8 hours to do it, and I could be doing something else. So we need to think really carefully about it. So some of you may be thinking, what was it that I actually changed if it wasn't, one of those GC parameters to make the fast system faster? And it turned out what it was. I was sort of banging my head against the wall, and I was trying everything. And I was running JMeter on a different machine, because of course you should never ever run JMeter, which drives the load, on the same system as the system that's getting the load. But when I put them on the same machine, it started going way faster. And the reason is that, on a modern laptop, I couldn't actually drive enough load that I was maxing out the CPU. So what I was maxing out was the network connection. And so once I removed that bottleneck of the network connection, everything went faster. And so the moral of the story is Gene Kim wasn't thinking about performance tuning, but any improvement made anywhere besides the bottleneck are an illusion. You know, you think you're doing all this good stuff, but if it's not the bottleneck, it doesn't matter. The other thing to bear in mind is that time kills all performance advice. So that advice about garbage collection from 15 years ago just doesn't make any sense in general. But there are, even with that, there are a few things to take away from this experiment. One is GC is your friend. It can rearrange the heap, so it's a good investment. You absolutely need to find the bottleneck, otherwise everything that you're playing with doesn't make any difference. And you have to do the experiments. And there's such a problem, I think, because none of us have time and energy to know everything. And all of us should be learning from experts. So of course we want to find advice about how to optimize. And that's kind of good, but it's also the third pitfall. Because there is so much bad advice about performance optimization. And a lot of it was good advice once, but it's just not anymore. So you can still find advice that says what you should do in Java is you should make one huge mega monster long method because method dispatching is slow. That was, I think, maybe true in like 1.1, 1.2. Now it's the opposite. The JIT can much more easily deal with small methods as well as the humans working on the code base. Another piece of totally stale advice is that you want to help your garbage collector. You don't want to generate garbage. So what you want to do is you want to reuse your objects. Just sort of swap around the data, forget about immutability, and that will make things go faster. No, it won't. It will make them go much, much slower, as well as being a nightmare for all of the humans using the code. Because on a modern garbage collector, if something isn't used anymore, collecting it is basically free. If it lives for a long time, collecting it is really expensive. And of course, we all know tuning the GC is kind of intimidating, and we really want to find the answer on Stack Overflow. So then you end up with these sort of folklore command lines that just get passed forward. And Ben Evans has a story that when, at New Relic, when they analyzed all of the sort of the parameters that people were using, they found something like 8% of the internet, or something ridiculous like that, had set, I think, some part of the heap to something like 817 megabytes. And they were like, that's a really weird number. And what it was supposed to be 8172, and someone at some point had made a typo. And this number had propagated from this one little typo. No one had actually looked at the number, realized what had happened. Instead, they just cut and pasted it forward across a huge portion of the internet. Sometimes it's a little bit more subtle. So it is classic performance advice that you shouldn't concatenate strings with plus equals. You have to use something like a string builder instead. Who here thinks this is good advice? Who? Yep, some hands. Don't be afraid, this one isn't a trick question. Who here thinks this is bad advice? OK, about the same number. Who's too scared to answer because they don't believe me when I said it wasn't a trick question? OK, most of the rest of you. And I think with this one, what makes it sort of hard to answer is the context. In general, that is correct advice. But in our context, it may be wrong advice. Jeff Atwood coined this phrase, micro-optimization theater. And I think it's something that's so easy to get drawn into, which is we think, I've seen something that I know is slow, so I'll just fix it. What could possibly go wrong? So I did a little experiment to try and see how much impact the plus equals would make. So if you have a method like this, if it's in a loop, we all know it's probably going to be slow. So I went back to DayTrader, that benchmark I was using, and I found a place that was doing string manipulation, and I changed it. So it was in a loop, and I changed it to use a plus equals because I knew that would be slow. And yeah, you can see in a loop, definitely going to be a problem. And I had the same thing as I did with my other experiment. And I'm preparing the talk, and none of my experiments are doing what I'm hoping, and I'm losing the will to live. Eventually, I worked out I'd carefully de-optimized this method. The method never, ever, ever got called. And so if I'd done the opposite, right? Like if I'd been working away and I'd spotted that problem code, and I was like, I'm going to be a hero, I'm going to fix that code, it wouldn't have made any difference at all. Now, there's still sort of a thing here of like, every little helps, right? Every optimization that you're doing is good, right? It's not making it worse, it's still making it better. But the problem is every optimization that you do is another optimization. It's a bit of your time and energy for another optimization that maybe would make more difference. So I think about this a lot when I think about when I'm traveling to conferences. I'll always make a point of not taking a taxi to the airport. I'll take public transit to and from the airport. And sometimes that's easy. Sometimes it's actually really hard and kind of complicated and a little bit scary. But I feel like a hero, right? Because I'm like, I have saved so much carbon by not taking a taxi in order to then go and get on a plane that spews out so much carbon that it doesn't really matter what I did with the taxi almost, because and then sort of going back to well, surely it would be better to take a taxi, surely it would be better to take like a train and then a plane than a taxi and a train. Probably yes, but the problem is if I feel like so much of a hero for taking a taxi that I think I'm allowed to take a plane, it kind of it doesn't work like that. The other interesting thing about the plus equals example is that if you had this code, because that loop is really predictable, the JVM will sort it out for you, and it will make it okay. And so what that means is that this code, which I think is much more readable than a string builder, is totally fine. Because the thing is, there's a lot of incredibly clever people in the JVM team, and they have far, far more time for optimizing than any of us. And the scenario that they're going to optimize for is clean, typical code. So if you do an absolutely bonkers optimization, you're going to be off that golden path of things that they're optimizing for. So when it comes to writing code, you want to be as normal and as clean, as idiomatic as possible. OK, so now that you know what all of the things not to do, what actually should you do? Because it would be kind of depressing if you came to this talk and you left thinking, optimization is really important, and I know exactly how not to do it. So there are some things that I would sort of suggest as starting points. One is you're going to have tools. We used to think about these as sort of monitoring tools, diagnostic tools, but really what we're trying to do is observe our systems. And because what you can optimize is limited to what you can observe. So now, all of these observability tools, this sort of new breed of observability tools, are actually really going to help us with some of those optimization considerations as well. So if you've got observability, you're in a good place. Unfortunately, very few of us actually have observability in production. But still, we're sort of going down that road. The other tools that you can and should be looking at are method profilers. So Visual VM is a good one. Mission Control has it if you're on OpenJ9. There's a tool called IBM Health Center, which I mention partly because it's really cool and partly because I wrote it. That you also want to be looking at things like flame graphs. I can't find a good recommendation for a flame graph tool for Java. It feels like there must be one, but I don't know it. The other thing that you're going to want to be looking at is GC analysis. So that doesn't mean that you use your GC analysis just to drive down the GC times, but you definitely want to know what's going on. So something like GCMV is a good choice there. For heap analysis, Eclipse MAT is probably the standard tool. You may also want to look a little bit sort of higher up the value chains for something more integrated, like an APM system. Most of these, unfortunately, are not open source because they are that little bit higher up the value chain. GlowRoot is open source. I haven't used it personally. Or you can be looking at things like New Relic or AppDynamics or Dynatrace, all good choices. And then, of course, you're probably not having a single system running in its own little thing. You're probably going to be having a distributed system. So you're going to want to use something like Zipkin or Jaeger. But let's think a little bit more about that distributed tracing and what the implications of that are. Because hopefully I've persuaded you that micro-optimizing is really bad. You have to measure the whole system to find the bottleneck before you invest time in one part of the system, because you need to know where you should be spending your time. So what if your whole system looks like this, and you were promised that as a microservices developer, you only had to look at your little service. You didn't have to look at the whole system, because that's the point of microservices. And so if you optimize your microservice, does that mean that you're micro-optimizing? And if so, then what do you do? I think probably there's sort of an organizational level decision then to say, OK, spend a little bit of time optimizing your microservice maybe, but we do kind of need to know the whole system of the whole context of the system in order to figure out where we should be putting our resources and which microservices need optimizing. The ones that are getting a ton of traffic and slowing everything down, we need to find that bottleneck before we go down into the service level optimizing. Another thing to sort of get into your toolbox is a little bit more of a sort of a statistics and queuing theory understanding. So Charity Majors always says, she's talking in the context of observability, but I think it applies to performance as well, nines don't matter if your users aren't happy. And what she really means by this is don't be sort of seduced by the averages. Don't be seduced by aggregation and think you've got the whole picture. Because when it comes to performance, averages are kind of interesting, but what you really need to know is the distribution. If most of my requests finish fine, but 5% of my requests take 10 minutes, that's 5% of my users that I've lost that are maybe never coming back. I need to know that, even if overall I'm completing in 100 milliseconds. So it's worth doing a little bit of reading into queuing theory. Queuing theory, what it tells us is where the disasters happen. So queuing theory tells us, well, what happens if on that edge case, this stacks on top of this stack on top of this stack, and then the whole thing collapses? And this is really important to know, because those disasters, they can make users annoyed, but they can also be really, really directly expensive, because we've all heard the stories of, I did this little thing, and then I got this Amazon bill, and then I had to file for bankruptcy, because these cloud costs can be really astronomical. And even if we don't get into that disaster scenario, we kind of need to be looking at them because it's money. OK, so my colleague, when he came in, he said, I'm only here for the polar bears. And I'm conscious that I've been talking for 44 minutes, and there hasn't been a single polar bear yet. And you can't ask for your money back because you've already lost the time. So what do you do? Well, here's the bears, so it's all OK. I have 2 kids, and like all kids, they drive me bonkers. And one of the things that they do that I get so frustrated by is they'll be watching TV, and then they're done watching TV, and so they just sort of wander away. And I'm like, but you left the TV on. You're not using that TV. And what are you doing? And it didn't work, and it didn't work. And so eventually I lost it. And I told them that every time they left the TV on, a polar bear died because of the climate implications. They were slightly traumatized, so I do not recommend this as a parenting technique. But it's sort of, without the trauma, hopefully, it's a little bit the same for us at work. That if we're doing things and they're just wasting resources, that's bad. Even if it wasn't for our conversion rates and that kind of thing, we should be avoiding waste. And that means we shouldn't waste electricity. And also, we shouldn't be wasting hardware. So we should be trying to be as efficient as possible in how we consume the hardware. And this really matters because our industry has quite a big environmental impact. Data centers alone, even leaving aside the sort of the hardware, which is actually where quite a lot of the carbon goes, data centers alone use 1% to 2% of the world's electricity. So it's big. And we, with our actions, with our optimizations, can make a difference and get that number down. So in practical terms, what this means that we have to be doing is we need to be responsible for fewer devices. So the way we do that is we make programs that have higher efficiency, that have lower footprint, so we can stack them more tightly into the virtual machines. We need to have more support for multi-tenancy in all of our programming models so that we don't end up with the one application per Kubernetes cluster model. We also need to be trying to make sure that our hardware lasts longer. So we need to be thinking about, in terms of our relationship with the hardware and how many hardware resources we use, we need to optimize for longevity. And ideally as well, this is sort of a broader industry thing, but ideally if we got to the end of planned obsolescence, I think that would make a really big difference. So with all that said, takeaway, it is in all of our powers to optimize, and it's actually quite a fun technical challenge. You can be successful optimizing as long as you follow the sort of the one golden principle, which is measure, don't guess. But don't get so excited and enthusiastic for saving the polar bears that you optimize in the wrong places. Really focus the optimizing on where it's going to make the difference, on where it's going to move the needle. And with that, thank you. And those are the slides. And I think we've got time for a couple of questions. Oh, I think there's one over there. This is where the trick questions get turned around.
Yes, I had a question about, so how do you sort the good from the bad when you're reading about optimizations online? So you gave the example of not reusing objects. In the games industry, for example, everyone goes on about object pooling over and over and over again. But I'm sure that there are lots of situations where that's a really bad example. How do you process that information?
I think it's back to, ideally, everything that you would do, you would validate with an experiment. Of course, there's only so much time in the day. So if every time you read something on the internet, you went away and did an experiment, I mean, I guess the good news is you wouldn't read very much internet because you'd be busy spending it. But you have to have sort of a pre-filter, and time is a goodish pre-filter. But then you're right that it does become overwhelming. So if you can get a habit and a technique for doing quick experiments just to validate, that's good. But there's sort of a pitfall there too, which is micro-benchmarks are in general how you would sort of validate these things, and you'd say, okay, well, I don't want to try this on my whole application because that's quite complicated. Let me just find something that just does a lot of GC and LC, and then that will give you the wrong answer. So for example, if you, in the context of GC, you can get some things that just create objects, but they don't ever measure how the objects are talking to each other, so they will give you the wrong answer. So what I would suggest is try and do quick experiments, try and get like a little setup so that you can just quickly see the impact, but it's got to be as production-like as possible, and it's got to not be micro-benchmarks, unfortunately. Any other questions?
Yeah, so when do you decide that you need to optimize? And when do you see that you need to stop optimizing?
Yeah, that's a super question. And I think you can go wrong in both directions. So sometimes you decide you need to optimize when your manager comes to you and tells you that everything is terrible and it's your fault and that you need to optimize. That's probably too late. But it certainly is worth thinking. You don't want to go the other way either and say, right, we're starting this greenfield project and we're going to get our response times down to 10 milliseconds. Well, but do we need that? So I think probably what you want to do is avoid the obvious terrible anti-patterns that don't actually improve the cleanliness of your code, but otherwise sort of go at least sort of part of the way through, see if people are using it, and then once you can see that people are using it and see how they're using it, that's when you probably want to start thinking about, okay, so is this good enough, and what does good enough mean? And try and get a little bit of a validated answer for what good enough means, and then prioritize. So then focus on, okay, what do we do to get to good enough? And then after that, let's not keep going. Let's switch our attention to the next most pressing system or the next most pressing problem, which maybe isn't performance. But yeah, that's both of those questions. I wish I knew the answer. Unfortunately, nothing is easy, or we'd all be doing it. And I do have a red flashy thing, so I think we better stop. But happy to answer more questions in chat or on Twitter or anything. And thank you very much.